Um, so let me, yeah, Brian, any advice on how I should address that? It seems to be working on my end. Brian, should I try restarting or? Okay, great. Awesome. Hello, everybody. It sounds like perhaps my microphone had been muted, but it sounds like it's working now. So I was just saying that today we're going to be covering kinematics and projectile motion. What is kinematics? Kinematics is just a fancy word for the study of motion. So we're going to start by defining 5 key kinematic variables, which are variables that describe motion. All right, so let's start with a thought experiment. Let's say that you agree to meet with your friend in Central Park 30 minutes from now. What are some pieces of information that you would need to determine whether you would be able to make it to meet your friend on time in 30 minutes? All right, feel free to type some things into the chat as you think about it. All right, what are some key pieces of information you would need? Well, here are a few. How far away is Central Park? And, perhaps both how far is it in a straight line from where I live, but also how far would I actually need to drive to get there? Or how far would I actually need to walk, depending on how the city blocks are laid out? How fast will I be able to drive? Taking into account not just the maximum speed, but also stoplights and getting stuck in traffic, things like that. And what time will I actually be able to leave? If I'm taking a bus, for example, will I need to wait 10 minutes until the next bus leaves? Or do I still need to gather my stuff and put on clothes before I head out the door? So those are some things to think about. And these relate to some of the kinematic variables that we're going to be talking about. Okay, making the point mainly that these are sort of some common sense notions. Let's talk about distance and displacement. These are both measures of length, and so they both have length units, so we'll stick with meters. But distance and displacement are not the same thing. If anybody knows the difference, feel free to put it into the chat. And if you have any questions as we go, type your questions into the chat and I'll be happy to answer them. All right, let's think about 2 ways we could measure a length between our starting point and our ending point. The first one is we could take into account the actual path we need to follow. So for example, maybe I come out of my driveway and then I go around the corner and I need to get on the main street. I take the main street to my destination, sort of over here, and then maybe finally make it to my destination. All right, that's one way. Another way is I could just think about how far is it from my start point to my end point in a straight line. Okay. Oh, and I'm having a glitch in the classroom where my pen's not showing up, so I'm going to refresh quickly and should be back in just a sec. Right. So I am back. Fantastic. So we talked about 2 different ways to measure the distance between these 2 points. Okay, yeah, great. And I see a question from the chat. Are we going to look at AP physics problems? A great question, Harshal. I think that I was answering this when my mic was muted at the beginning. The topics we're covering today are going to be a little bit more foundational or introductory. So they're a good introduction to things that are covered on AP Physics, especially AP Physics 1. But the questions and examples we'll be doing could show up on the AP exam, but would be on the easier end of the types of problems you would see on AP Physics 1, although they could definitely appear. So I hope that answers your question. All right, so definitely a good intro to AP Physics if that's something you're going to be taking next year or next semester. Alrighty. Um, so distance and displacement, though, are not the same things. Distance is a measure of the path that an object actually takes. So this blue line would be an example of distance. Okay, whereas the difference between the initial and the final positions, the distance between the start and the end point, is called the displacement. Okay, so notice that the distance will always be greater than or equal to the displacement. Um, Notice also that distance is just a number. It's just how long is the path that you took. Displacement is what we call a vector, which means that it includes not just a number, but also a direction. So in this case, the displacement is this purple arrow that I drew. It says how far you had to go and in which direction to get from the start point to the end point. So we can also have an equation for the displacement, which is displacement equals the final position minus the initial position. Okay, this equation that we have right down here. Notice that I've bolded the displacement and that, I've bolded the displacement to show that it's a vector. I see that Johan Lakshman asks, would this be sufficient for the SAT physics exam? Similar comment, these things definitely will appear on the SAT subject test on physics, but there will also be things on that test that we're not going to cover today. But this is definitely a good introduction to some of those topics. All right, so let's see two examples of distance and displacement. I'll let you guys work these out. I'll let you guys take a minute to work them out, and then we'll cover them together. So pull out a pencil and paper if you haven't already. Cindy runs 4 laps of a 400-meter track. What are her distance and displacement? Okay, and the second question, Thomas walks 300 meters north, then 400 meters east. What are Thomas's distance and displacement? Okay, work those out a bit on your own, and then we will cover them together. All right, it is okay if you are not finished yet. And if you're watching this video after the live stream, feel free to pause it and continue working. But let's go over it together now. It's okay if you didn't finish working on the problem. I just wanted you to start thinking it through. Okay, good. So we're getting some feedback. So first, so Harshal says 1,600 meters. Let's talk about the distance first. Okay, so the distance that Cindy covers, she runs 4 laps times 400 meters per lap, which equals a total of 1,600 meters, right? So fantastic, just like Harshal said. And then let's talk about displacement. All right. Oh, good. And we're getting some feedback about Thomas as well. So Cindy's displacement, well, she ran 4 full laps. So let's say she started at the start line. She goes around 4 times, and she finishes at the same place that she starts. So her displacement equals final position minus initial position. And since those are the same place, her displacement is 0 meters. All right, now let's do Thomas. I'll start by drawing a picture. Always a good place to start. Thomas walks 300 meters north, which I'll represent as upwards on the whiteboard. And then he walks 400 meters to the east. So what are his distance and displacement? All right, fantastic. I love all the feedback we're getting in the chat. Thank you. All right, lots of right answers in there. Looking good, looking good. So first, let's talk about Thomas's distance. All right. So distance, remember, is the length of the path that he actually takes. So Thomas first walks 300 meters north, and then he walks 400 meters east. Okay, so the distance is 300 meters plus 400 meters, right? That's the length of the path he followed, which is 700 meters, which I saw that some of you had said in the chat. Fantastic. I see that Harshal had said so, Johan had said so. All right, and then what about Thomas's displacement? Okay. So you might recognize that this is an example of a 3, 4, 5 triangle. It's a Pythagorean triple. So maybe you're remembering this from your geometry class. So I know that this is this side, the hypotenuse of the right triangle here is 500 meters. If you didn't remember your Pythagorean triples, we also could have used the Pythagorean theorem to find the length of that third side. But it is 500 meters. So Thomas's displacement is 500 meters. All right, and lots of people in the chat are saying 500 meters, but is that the full answer for the displacement, or is something missing? What's missing? It's 500 meters, that's right. But it's 500 meters to the northeast. Okay, good. So we need to say which direction Thomas is walking in to fully specify what the displacement is. So we could say it's 500 meters to the north and to the east, right? We need to say which direction. All right, and we could do some trig to find the exact angle, things like that, but that's not too important here. Now let's talk about speed and velocity. Right? Speed and velocity are both measures of length per unit time, and they both have units of meters per second. You can think of them as the rate at which a length changes. Okay, good, yeah. I see that Hung says northeast. Fantastic, that's right. Okay, so we can think of speed and velocity both as measuring changes in length or distance or position, but they're not the same thing. Okay, speed is a scalar quantity. Scalar is another word for just a number. Okay, speed is a scalar, which means it has no direction attached. So the formula for speed is just distance divided by time. Velocity, meanwhile, is a vector, which means that it includes both magnitude and direction. So your average velocity is your displacement divided by time. And we have a formula for that your average velocity is displacement over time. And notice that I've made both velocity and displacement in bold. I see that Harshal asked, would you get marked down on an exam if you didn't mention Northeast? That depends on your teacher and sort of how harsh they are. And perhaps also the way the question is asked. If the question just said, what is the magnitude of Thomas's velocity? Then you could say the magnitude of his displacement. You could say that the magnitude of the displacement is just 500 meters. But if it asks for the displacement, you should say that it's 500 meters and to the northeast. And your teacher could mark you down if you didn't say so. Is time a vector for the second formula? Great question. Time is not a vector. Maybe you could think it like, time doesn't really have a direction associated with it, at least not in the same way as displacement and velocity and acceleration do. In a certain sense, time kind of, does it point forward maybe, right? Time is always pointing forward in time, but it doesn't have a direction in the same way as the others, and so time is a scalar, okay? But that's a very good question. All right, and that's because there's only one dimension to time and multiple dimensions to space, but this starts to get a little bit more abstract, but time is always a scalar. Very good question. All right, so this is speed and velocity. Let's now look at some examples contrasting speed with velocity, and remember these formulas, that the average velocity is distance divided by time. Okay, we'll need that to do these problems. Oh yeah, good question, Hung. So can we still divide a vector by time, even though time is a scalar? Yes, absolutely. So vectors can be divided by scalars. Yep, that's a very good question. And it works the same way numerically as division ordinarily works. And the result that you get will still have the same direction as the initial vector did. So if you divide a vector which says, if you have a vector which is 10 meters per second to the east, and you divide it by 2, your resulting vector is 5 meters per second still to the east. Oh, great question. So for Cindy's displacement, do we have to write the direction? And then double question marks from Bosvi. Yeah, that one's tough, right? Because she ended up back in the same place where she started. So, so she had a displacement of 0 meters. And the one time you don't need to say which direction is when a vector has a value of 0 or a magnitude of 0. And that's because think of it as an arrow with no length. Well, which direction is it pointing, right? So when it's 0, there's no direction just because it's 0. And so there's no way for it to point in a direction. Anytime a vector isn't 0, you'll need to say which direction it is. And technically, there's still sort of a direction. There's just no way to say which way it is, because it's kind of, because it's 0. But again, that gets a little more abstract. So you can just think of it like if it's 0, you don't need to worry about the direction. All right, very good question. And we'll see that some more on these examples. So Cindy runs 4 laps of a 400-meter track. It takes her 5 minutes and 20 seconds to complete those 4 laps. What are her average speed and her average velocity? Okay. And then second question, Thomas walks 300 meters north and 400 meters east. It takes him 700 seconds. What are his average speed and average velocity? I'll give you guys a minute to work these through, and then we'll go over them together. And if you're watching afterwards, feel free to pause your video. All right. And yeah, feel free to put your answers into the chat. And it is okay if you haven't finished. I hope you at least got started, or at least started thinking about it. And so now we'll go over it together. Let's first talk about Cindy, and let's talk about her speed first, because that comes first in the question. All right, what is Cindy's speed? So remember, speed involves distance. Okay, speed equals distance divided by time. So actually, I'll write that as an equal. Speed equals distance divided by time. And we know that the distance that Cindy covered is 1,600 meters, since she did 4 laps. All right, so 1,600 meters. And then 5 minutes and 20 seconds. Well, I know there's 60 seconds in a minute. So 6 times 5 is 30. So 60 times 5 is 300. And then 20 seconds. So divided by 320 seconds that it takes her total to run the 1,600. All right. So 1,600 divided by 320. What does that come out to? And I see, very good. Yeah, I see a couple of answers in the chat. I see that Johan and Ruthvik and Harshal have all said, probably some others as well, have all said that this divides out to 5 meters per second. Fantastic. That's about 12 miles an hour, 11 or 12 miles an hour. Pretty good. And 5:20, that's a pretty good time for the 1,600, especially if, say, Cindy's like a high school athlete. Pretty good. She'll win some meets with that. For those of you who run track. All right. Or whoops, not displacement, but what I meant to write here was what about Cindy's velocity, which depends on her displacement. Okay. What was Cindy's average velocity? Very good. I see people saying that her average velocity is 0 meters per second. Okay, so I'll write V average. And I'll write it with a little arrow over top to show that it's a vector, equals displacement divided by time. And Cindy's displacement was 0 meters. And I could write it with a little arrow to show that it's a vector 0. But again, there's still no real direction since she didn't go anywhere. divided by 320 seconds. But if she didn't go anywhere, then her velocity is still 0 meters per second. Okay, fantastic. Her average velocity. Fantastic. So she had velocities along the way, right, that were not 0. She was heading, with like 5 meters per second east and then 5 meters per second west, but the average is 0. Okay, because the east and the west kind of cancel each other out. Now let's talk about Thomas. First is speed, right? Remember, speed equals distance divided by time. All right, and we said that the distance that Thomas covered was 700 meters. That's the length of the full path that he took. So he covered 700 meters total, and I decided to say that it took him 700 seconds to make the math nice and easy for myself. If you make up the problems, you can make them easy. So equals 1 meter per second. Very good. Very good. I see that coming in the chat as well. Bosby says that Thomas's average speed is 1 meter per second. Okay, this is an average. And then what about Thomas's average velocity? Okay, sticking with my color coding. So we have that the average velocity that Thomas is walking at is his displacement divided by time, right? Where displacement is a vector. And we said that Thomas's displacement was 500 meters and is going to take him 700 seconds to walk that far. And yeah, this comes out to what, 5/7 of a meter per second, and 5/7 is about 0.7. So something like 0.7 meters per second. Okay, fantastic. So 0.7 meters per second. And once again, is there something missing here? And good, I see people have been typing into the chat that it's 0.7, and some people have been remembering to include the northeast, and some have been leaving it out. So yeah, remember that this is 0.7 meters per second, and since it's a vector, we have to say which direction it is as well. Yeah, fantastic. Fantastic. Yeah, thanks everybody. You're doing very well. I can tell that you guys are following along. So next is acceleration. So in the same way that speeds and velocities were differences in displacement and distance, acceleration is differences in speed and velocity, specifically velocity. Okay, so acceleration is a measure of length per unit time squared. So meters per second squared are the units. And sometimes people pronounce this, most common is meters per second squared, but sometimes people will pronounce these units as meters per second per second. Okay, and you can think of this as the rate at which a velocity changes. Okay. So for example, if we have some velocity v1, and then sometime later we have a velocity v2, right? What's the difference between v1 and v2? Right? What's the difference between these two? Okay, the answer is the difference is this. Right? This purple arrow that I just drew is the difference between v1 and v2. And mathematically, this purple arrow is, it turns out, v2 minus v1. Okay, and people will often write this change in the velocity just as delta v, which means v2 minus v1. All right, so the velocity increased, and I'm representing that with the purple arrow. So acceleration is a vector quantity. It includes both magnitude and direction, and it's change in velocity divided by time. That tells us the average acceleration. And again, I've put both the acceleration and the change in velocity in bold to indicate that they are both vector quantities. All right, and time is a scalar. Unlike with displacement and velocity, there's no special name for the scalar analog of acceleration. You would just say the magnitude of the acceleration if you wanted to refer to the scalar version. Okay, let's look at a couple of examples. Cindy runs a 100-meter dash. Let's say that it takes her 12 seconds, and her final velocity is 9 meters per second. What is Cindy's average acceleration? Okay. And then Thomas bikes north for 1 minute. He starts from rest and accelerates at a rate of 1 meter per second squared to the north. What is Thomas's final velocity? I'll give you guys a minute, and then we'll go over them together. And yeah, feel free to put your answers in the chat. All right, just like before, it's okay if you're not totally finished yet. Remember the formula we have for the average acceleration. A average equals the change in velocity divided by the time. And remember that change in velocity is the same as what the final velocity was minus what the initial velocity was. What were Cindy's final and initial velocities? Well, we said that she reached a maximum speed at the end of her 100-meter dash of 9 meters per second. Okay, so 9 meters per second. And she started from rest. During the 100-meter dash, you start crouched down in the blocks, and then the gun goes off, and you start running. So she starts from 0 meters per second and goes up to 9. So final is 9, initial is 0. And we said it took her 12 seconds. That's pretty good for the 100-meter dash. Okay, 12 seconds. So then, what's 9 divided by 12? This is a fraction I could simplify. I could cancel a 3 out of both the top and the bottom. And I get, this simplifies to 3/4 meters per second squared. Or if I wanted to put this in decimal form, I could say 0.75 meters per second squared. All right, fantastic. Okay. And with the 3/4, right, I divided a 3 out of each. So 9 became 3 and 12 became 4. Now let's talk about Thomas. He bikes north for 1 minute. He starts from rest and accelerates at a rate of 1 meter per second to the north. Notice how the acceleration was given with a direction here. So it had both a magnitude and a direction since it is a velocity. Okay, what is his final velocity? So once again, we can use the same formula. The average acceleration is change in velocity over time. In this case, instead of being given the change in velocity, we're given his acceleration. We're told that his acceleration is 1 meter per second squared, which means that on average, it will still be 1 meter per second squared. Okay, so I can say that 1 meter per second squared equals v final minus v initial divided by the duration of time that Thomas bikes to the north, which was 60 seconds. Now I will multiply both sides by 60, or by 60 seconds. And so I get 1 meter per second squared times 60 seconds equals v final minus v initial. And we actually said that Thomas started from rest, so v final minus 0 meters per second. 1 times 60 is 60, so 60 meters per second. And the units are meters per second now because the seconds here canceled with one of the seconds in the denominator of the meters per second squared term, equals Thomas's final velocity. So it says he's going at 60 meters per second. So now, is that realistic? That's pretty fast. That's like 120 miles an hour. So maybe if Thomas is biking on a motorcycle, So let's say he's on a motorcycle to make the example realistic. So let me see. I see that there were some comments coming in. So first of all, yeah, fantastic. Lots of people were typing in some correct answers. So thank you for passing those along. I see that Ane Bade asks, is projectile motion a form of motion experienced by a projectile under under the action of gravity only? Yeah, that's exactly right, Ane. And we're going to come to that. Maybe we'll get there in 5 or 10 minutes in today's lecture. But yeah, fantastic question. And Vasvi asks, so is 100 meters unnecessary information? Yes, absolutely. In this first example with Cindy, the fact that it was a 100-meter dash didn't actually factor into her acceleration at all. We were able to solve it just based on the time that it took and her change in velocity. That's what determines average acceleration. We would have needed to know the distance if it had asked us something like, what's her average velocity, right? If instead they had asked, what's the average velocity, then we could find that, using the distance and the time. Okay, so yeah, great question, Vasvi. And they asks about air resistance. We'll get to that more when we talk about projectile motion. And then, yeah, fantastic. I see a bunch of, good answers to the question about Thomas. And they also asked about launch angles and the range of an object. Yeah, fantastic. We'll get into that more when we reach projectile motion, but the equation that you wrote for the range is correct. If you assume, a launch angle of theta. That's the correct formula, absolutely. And yeah, typically angles are between 0 and 90, just by convention, because imagine if you had an angle bigger than 90, you're really just shooting it the other way. So you could do that as well. That would also be valid. All right, but again, we'll get to that more when we talk about projectile motion. All right, one more example of acceleration. Cindy runs 1 lap of a circular 400-meter track in 66 seconds. What is her average acceleration? Okay, I'll give you guys a minute to work on that. And Smith, thank you. I see a comment that I am a very good teacher. I appreciate it. That makes me feel good. Thank you for saying so. All right. So what is Cindy's average acceleration if she runs in this circle? Okay. All right, so what is her average acceleration if she runs in this circle? Well, so once again, I'll just use the formula that we learned for the average acceleration. Right, remember that it is, is the change in her velocity divided by time. Okay, and what was what was her change in velocity when she ran around this track? Let's say that she was running at a constant speed. We didn't say that in the way the problem was stated, but let's say she's running at a constant speed. That means when she finishes, she's going the same speed she was just after she had started. So her change in velocity would be about 0 meters per second. Now, maybe she's running a little faster at the end than the beginning if she was sprinting at the end or something, right? But it's about 0 meters per second. And it took her 66 seconds. Okay, so this would mean that her average acceleration is 0 meters per second squared. Now, just as an example, let's say that actually at the end she was running something like 5 meters per second faster than when she started. Right, then we could just divide these two numbers, and I would get something like 0.1, roughly, meters per second squared. Okay, and I would now have to say which direction this was in. So depending on which way the track was facing, so 0.1 meters per second, and the direction would depend on which way the track is facing. So maybe that's to the east, right, or something like that. Right, we'd have to look at a map of the track to know. Okay, but basically 0 meters per second. Let me ask you this. Is her acceleration while she's running always equal to 0? So even if the average is 0, is she always accelerating only at 0 meters per second squared while she's running? What do you think? So the average is 0, but is her acceleration 0 during the process? Let's say for simplicity that Cindy is running at a constant speed. All right, let's say your speed actually is constant. So first she's running upwards, right, like this. Now she's running to the side. Now she's running, down. She's running around the track like this. So these arrows represent Cindy's velocity at different points along her run. Okay, which direction is Cindy's acceleration? Okay, the average was 0, but it's not always 0, right? Cindy's acceleration is actually towards the center of the circle, like this. All right. Since even though she's running at a constant speed, her velocity is changing. Harshal, could you elaborate a little bit on your question? You said you don't get the 0 meters per second. Oh, I see. You don't understand why her change in velocity is 0. It's because she's running at constant speed. So both at the beginning and the end, she's running at about the same speed. Yep, good question. All right. And yeah, good. Lots of people in the chat are saying, so yeah, it's variable. Her acceleration is variable because her direction keeps changing. So even if she's running at a constant speed, she's always changing directions as she goes around the circle. And because she changes directions, that means that her velocity is changing, since velocity includes direction. And so her acceleration won't be 0. But since the acceleration always points towards the center of the circle, good. And I see people saying in the chat that that the acceleration is towards the center of the circle, which is at right angles to the velocity. And so therefore, the accelerations cancel out, right? Since they're all in different directions and she goes around a whole circle and all the different accelerations cancel out. All right, fantastic. So the average is 0, even though the so-called instantaneous acceleration at different points is not 0. Fantastic. And yeah, good, Vasvi. I hear somebody in the chat says acceleration is 0 with the direction towards the center. Good, but there's also 0 work done. Yeah, that's absolutely correct. We're not going to get into work in today's class, but that's absolutely right. Like the centripetal force, so to speak, wouldn't do any work because it's at right angles to her displacement. But that's a bit of a separate topic. All right, so let's say you're driving a car, and let's represent that as the car moving to the right on the slide. What are some actions you could take to apply an acceleration to the car? Okay, what are some, and feel free to type some things into the chat. What are some ways that we could change the car's velocity? I'm sitting in the driver's seat. What actions could I take to apply some sort of acceleration to the car? Okay. Feel free to put some ideas in the chat. One idea is we could step on the gas. All right, so stepping on the gas will apply an acceleration. If the car is moving to the right, stepping on the gas will speed the car up, right? Oh yeah, good question, Harshal. No, the question really should tell you assume constant speed. I think I just said that verbally when we were talking through the problem. So yeah, you're right. The question should say constant speed. That's a very good question. A very good point. Yeah, good. MX37 says you could brake, you could turn, you could use the accelerator. So yeah, those are fantastic suggestions. So first, if we're stepping on the gas, this will increase our speed, which will be an acceleration to the right. Okay. Okay. So if we're increasing the speed, so here was our initial speed, and we increase our speed to something bigger, right? And so we have an acceleration to the right. Okay, and another good example, something people I saw were saying in the chat was, yeah, we could use the brake, right? We could step on the brake if we want to apply an acceleration to the car, right? Applying the brake will decrease the velocity, right? and this corresponds to an acceleration to the left. Okay, so this will decrease the car's velocity. All right, and then finally, you could turn the steering wheel. Will turning the steering wheel change the car's speed? Okay. No, but it will change the car's direction. Okay, so turn the steering wheel. This will change the car's direction, and remember, when direction changes, that means that the velocity will change as well. Okay, so let's turn the steering wheel. So let's say that we turn the steering wheel to the right. All right, that means that we'll have an acceleration this way. All right, so what happens here is that the velocity will change directions, but keep the same magnitude. Okay, if we apply an acceleration at right angles to the velocity changes direction, but keeps the same magnitude. All right, and this was because the velocity and the acceleration were at right angles. So I'm showing that they're at right angles by using this little perpendicular sign. Okay, fantastic. And I see some great comments in the chat. People saying that we could throw the car into reverse. Yeah, absolutely. Risky move, but you could definitely try it. Yeah, good. I see somebody pointing out that we could increase the displacement while reducing the time, right? If we step on the gas, right, that's what would happen. We're accelerating. I see Ane saying, is the orientation of an object's acceleration given by the orientation of the net force acting on that object? Yes, that's absolutely correct. We're not talking about Newton's laws today, but that is absolutely correct. It's the net force on an object that determines what its acceleration is. So in the case of the car accelerating, when you step on the gas, this creates a force on the car forward, which accelerates the car forward. All right, and the direction of the acceleration also always corresponds to the direction of the change of velocity. And then I see somebody else asking about reversing the car. Yeah, absolutely, absolutely. You could do it. It's risky, so I don't recommend it, but you could. I see somebody else saying you could push the car from behind with some sort of mechanical force. Absolutely. So there are lots of ways you could do it. All right, you could drive down a hill, and gravity, for example, could pull the car down. Things like that. All right. Let's talk about uniformly accelerated motion next. So this is the study of motion along a single dimension with constant acceleration. All right, so we'll analyze this type of motion using 5 kinematic variables: displacement, initial velocity, final velocity, acceleration, and time. All right, so there are 5 of these variables. Typically, 3 of them will be given to you, and the question will ask you to determine the value of one of them. So since there's 5 total, this means you're given 3, you're asked for 1, and 1 will be missing. All right, so there are 5 possibilities for which variable could be missing, and so therefore you need 5 equations. And maybe if you've seen some of this in physics class, you remember how there can just be a really large number of equations. If you pick the wrong one, then you sort of solve out for a variable that you didn't want and have to plug that back in to a different equation, and it can get pretty messy. So remember, there's always one missing, and there's which variable is missing tells you which equation to use. So if A is missing, use this first equation. If the displacement is missing, then use the second equation, right? If the final velocity is missing, use the third one, and so on. So for your physics class, you'll need to know these 5 equations, and you should learn them by which is the missing variable corresponding out of the 5 key kinematic variables. Okay, so if A is missing, use equation 1. If T is missing, use equation 5, and so on. All right. Now, I know you haven't memorized all of these equations yet, but let's look at this example. Okay. Good. I believe I, yeah, pasted in. Oh, whoops. Yeah. Let's see. Um, okay. If that works. All right. Okay, that's fine. So let's do this example together. Um, so Joe drops a basketball off off of a cliff, and his sister Alice is standing at the bottom. Um, and Alice is very, she's the smart one, right? She's clever. She notices that the final velocity of the ball as it hits the ground is 30 meters per second. All right. So Joe drops this basketball. All right. And Alice sees that the final velocity is 30 meters per second. All right. So how high was the cliff? I'll give you guys a moment to work on this, and then we'll go over it together. Okay, how high is the cliff? All right. So you're probably not finished yet, but let's go over it together. So the key here is that we first want to figure out which variables we have and which ones are missing. So the variables in question are the distance, acceleration, initial velocity, final velocity, and time. We're given some of these values, but not others. The acceleration we know is -10 meters per second squared. That's just always what it is on Earth. Technically, it's 9.8, but 10 is usually close enough. All right, so that's just a value to know that the acceleration due to gravity on Earth is 10 meters per second, always downward. Do we know the initial velocity of the basketball? The problem just said he dropped it. So if it just says he dropped it, we can assume that means he dropped it from rest. Otherwise, it would have said he threw it with some velocity up or down or forward. Okay. The final velocity is the thing that the question asks us, or whoops, I'm sorry. No, Alice saw that the final velocity is 30 meters per second. Okay. So the final velocity is 30 meters per second, and we're asked for the height of the cliff. So the one that's missing is the time. Okay, so I want to choose the equation that has time missing. Okay, this, the one that I just circled, is the equation where time is missing. All right. So now let's plug into that equation. Yeah, fantastic. Good. I see some answers coming in through the chat. And we already identified our values, right? So plugging in here is easy. So the final velocity we know is 30. So 30 meters per second squared equals the initial velocity was 0 meters per second, right? So 0 meters per second squared plus 2 times 10 times d, the displacement that we're looking for. So 30 squared is 900, which equals 0 plus 20 times d. Now I can just divide both sides by 20, and 900 divided by 20 is 45 meters is the displacement. All right, fantastic. And that is the answer. And I saw a couple of questions come through in the chat about what's negative versus positive. And oh yes, good question. Absolutely. So couple of things here. When we say how high is the cliff, we probably mean just like, like what people would usually give a positive answer to how high is the cliff. But it's a very good point that if we wanted to, we could call the final velocity negative because the ball is moving down when it hits the ground. So if we wanted to call the final velocity negative, we would get a negative 30 inside of this expression. When it gets squared, it's still positive. And if we're calling the acceleration here negative as well, we would say that we get 900 equals 0 minus 20, which we absolutely could do it this way. And then we see that the distance is negative 45 meters. And the negative there means that the displacement was a downward displacement. Okay. The key thing is we just need to be consistent about how we use the positive and negative signs. Okay. So that's a very good question. And yeah, scalars actually can be negative. It just means like to the left versus to the right. So we can have negative scalars. Scalars just never say like to the north versus to the east, things at right angles to each other. But again, we just need to be consistent throughout the problem by how we do those. So we could say 45 or minus 45. I think people would normally say the cliff is just 45 meters tall. But we could say that there was a displacement of minus 45, meaning that it moved downward. Absolutely, as opposed to upward. All right, excellent questions. Let's see another example. Okay. Tanya, and we'll see, we'll see that in this one too. So Tanya accidentally drops her phone off the 86th floor observation deck at the Empire State Building. I looked it up. The height of this deck is 320 meters. And yeah, Lil Peep asks about whether it's positive or negative. Either one is possible. It just depends on which direction you choose as positive in the problem. So if you got that 45, if you got positive 45, that's equally valid. Yep. You could absolutely get that it's positive. Absolutely. Somebody had asked about could we sort of choose things such that it's negative, and you could do that too. So, all right. Ignoring, and to elaborate, that's based on which direction you choose to call positive in the problem. It's about how you define your coordinate axis. All right. Yeah, so if we define the top of the cliff as 0, and if we define downwards as being negative, then we say that the displacement is negative 45 at the end. Yep, so Hung is absolutely right. All right, so height of the deck's 320. Ignoring air resistance, how fast would the phone be going when it hits the ground? All right, what do you guys think? Which one of these 5 equations do we need to use? Okay, how fast will the phone be going when it hits the ground? So I think a good place to start is always to just list out our 5 variables, since we're going to need to know their values anyway. And since there were lots of questions about positive, negative, I'll illustrate that in more detail here. Yes, distance can be negative, or at least displacement can be negative. Usually people talk about distance as just being positive, but it's displacement that we're using in these formulas. And so, yep, so it absolutely could be negative. Yeah, so good question. Why do we know that the ball just moves straight downwards? So first thing is we actually don't need to know that to answer the question, but it's because he just drops the ball. If he had thrown the ball forward, then it would follow a curved path. Yep. In this case, he just dropped it, so it just went straight down. Good question, Ane. Yeah, good. So we say the height is 45 and the displacement was minus 45. Yep, absolutely. And we'll see a little more about that in this example. This is supposed to be, it's like a little sketch of, the Empire State Building. I don't know, that looks terrible. I'm going to just pretend I never drew that and get on with my life and just say that, okay, the building looks something like this instead, much better. All right, and let's call this 0 meters. And let's call this direction negative. All right, to sort of help clarify some of these questions you guys are having about positive versus negative. All right, good. And so hopefully you had some time to work on it while we were, while I was sort of goofing around and drawing and answering questions. So we're going to say that the downward direction counts as negative. All right. Yep, absolutely. So yeah, that's right. I wanted to, since the questions were coming in about negative, I wanted to address like height versus displacement, right? Since one, because yeah, that would determine whether you get positive or negative. All right, so let's go through this problem. The displacement, we know if we're calling downwards negative, is negative 320 meters, since the object ends up 320 meters below where it started. The acceleration is also downwards. It's negative 10 meters per second squared. Okay, the initial velocity is 0 meters per second, since Tanya dropped her phone. Yeah, good. And I'm seeing some good answers in the chat. Absolutely. The final velocity, we don't know. And that is what they ask us for. So this is what gets asked for. And the time here is missing. Okay. Or whoops. So the time here is missing. So I'll choose the equation here where time is missing. And that is this equation. Okay. So now I will plug in. I will switch colors. Or yeah. Right. So v final squared equals the initial velocity squared, which was 0 squared, plus 2 times the acceleration is minus 10 meters per second squared. And the displacement that the object fell through is negative 320 meters. Okay, minus 320. So 2 times 320 times 10 gives us that VF squared equals 0 plus 320 times 2 is 640 times 10 is 6,400 meters squared per second squared. And notice that the two negatives canceled out since both the acceleration and the displacement were downwards and therefore negative, so they multiplied to give us a positive number. All right, and so then I'll take the square root of both sides. Right, square root of v final, square root of 6,400 meters squared per second squared. And this gives me that the final velocity is 80 meters per second. Absolutely, yeah, fantastic. And I see there is some good answers in the chat. Okay, and since it asked for, it just said how fast would the phone be going? So we could say 80 meters per second. And if we wanted to give the velocity, we could say 80 meters per second downward, depending on exactly what the question asks. All right, yeah, fantastic. And I see some people getting it right in the chat. And I see somebody saying distance can only be 0 and positive, whereas displacement could be negative 0 and positive. Yeah, Smith, that's exactly right. That's exactly right. You got it. All right. Let's do one final example and wrap it up there. If a stone is dropped from rest, how long will it take to reach a speed of 100 meters per second? Okay, if a stone is dropped from rest, how long will it take to reach a speed of 100 meters per second? Okay. Yeah, and I see that as you guys are working, I'll answer this question from Hung, which is, do we normally use negative 10 meters per second squared, or could we use 9.8 meters per second squared? It just depends on how precise of an answer to your question you need. Typically, 10 is good enough. Like, that's pretty close to 9.8. But if you needed a more precise answer, you could use the more precise value. In fact, you might even need to be more precise than 9.8. For example, like 9.81, depending on exactly what you're doing. Like if you're worried about like precision artillery or things like that, then you might need an even more precise value than 9.8. But 10 is usually good enough. All right. So how long will it take to reach a speed of 100 meters per second? All right. So distance, acceleration, initial and final velocity, and time. Okay. Distance appears to be missing. The acceleration is -10 meters per second squared. It's dropped from rest, so this is 0. The final velocity we're given is -100 meters per second. And the time is the thing they ask us for. Okay, so I'm looking for the equation where d is missing, and that is equation number 2. So plugging in my values, I get that -100 meters per second. Good, and I see some correct answers in the chat. -100 meters per second equals initial velocity was 0 plus the acceleration, which is -10 meters per second squared, times the time that we're being asked for. So -100 meters per second equals 0 plus -10 meters per second squared times the time. Okay, now dividing both sides by -10, I get that t equals 10 seconds. All right, which I got by dividing both sides by -10 meters per second squared. All right, so it would take 10 seconds, which makes sense because every 10 seconds that go by, the velocity increases by 10 meters per second. It's 10 meters per second each second. All right, fantastic. Yeah, I will wrap it up there for today since we only have an hour. There's, yeah, definitely much more we could cover. And yeah, Harshal, good point. It could be 10.2 seconds if you used 9.8 instead of 10. So you can see it makes some small difference, 10 seconds, 10.2 seconds, just depends on how precise you need to be. So I hope this was helpful. These very same tools that we use to describe freefall, which is a type of projectile motion, can also be used for cases of projectile motion where there is some horizontal component to the velocity. To do this, you just break the motion up into its 2 separate components and treat those 2 components separately. So we would do it just the same way, both for cases of projectile motion like the ones we talked about, or for other types of cases that get a little more complicated. So you'll get into some of those more complicated courses in your physics classes. So yeah, feel free to send any final questions my way as we wrap up here. So type any final questions you had into the chat. So if there's anything I missed that you wanted to talk about, just type it right in there. I'll just close by mentioning a few real-world situations where we need to use projectile motion. If we wanted to design a robot to throw or catch a ball, you know, when I throw or catch a ball, I just use instinct or intuition. Like I just kind of can tell where it's going to go. But a robot maybe doesn't have that sort of intuition, so we would need to use these equations of projectile motion so that the robot could calculate where the ball will go. Similarly, when we describe the motion of the planets or distant stars, we use these same equations of projectile motion since for many celestial bodies, it's a pretty good assumption that acceleration is constant or uniform. For rocketry and ballistics, for example, to determine the range and trajectory of artillery shells, or to determine at a crime scene where the shooter must have been standing based on the angle and velocity that you infer from the penetration of the bullet, to figure out where he was standing, he or she. Determining the shape of roller coaster tracks. If you want to get that weightless feeling, then it has to have the right shape, and that's determined by these same equations that we learned in this class today. Or if you want to build ramps for bike or ski jumps, you need to know how fast the person's going to be going to know, you know, like how far and what angle to make the ramp so that they don't overshoot the landing ramp and they could hurt themselves. Okay, well, yeah, fantastic. I see lots of people saying thank you in the chat. Yeah, thank you guys. This was fun. I hope you enjoyed it. There's tons more physics out there, so there's a lot more we could cover. If you'd be interested in that, just let us know. It's something we could certainly, certainly explore. So yeah, thank you for the kind comments, and thank you so much for joining today's session. I hope it was fun, and I hope it was useful. All right. Yeah, great job. Thanks, guys.